This talk is about creating mathematical models from experimental observations. The experimental observation can be an accelerometer signal, a video, or some other time series. Humans and animals mostly learn from observations. Excessive exploration would be too dangerous. They also require very few observations to create a sufficiently accurate mental model. The mental model is not generative. We are not able to recall all details. Instead, we can recall abstract concepts like shapes, harsh or soft sound, and rough or smooth texture. We would like to create mathematical models the same way mental models are created. The difference is that the resulting model is a low-dimensional and parsimonious differential equation as opposed to rearranged neural connections in the brain. We consider an observation in the form of a measured initial condition and a measured trajectory, which was deterministically produced. The observation may not be repeatable only because the initial conditions cannot be easily controlled. The observation is usually high-dimensional. Our model also produces trajectories from initial conditions but is expected to be simple and low-dimensional. In order to make sure that the model and the observation are related, we need to construct functional connections between the observed initial condition and the model's initial condition, as well as the observed trajectory and the model trajectory. Such a connection can go two ways. It can map from the observation to the model, which is called an encoder, or from the model to the observation, which is a decoder. As a result, there are four possible combinations of connections which are called invariant foliation, invariant manifold, autoencoder, and equation-free model. These are the most commonly used names of the four architectures in the literature, but some are called differently in different contexts. Due to the assumption that the observed initial conditions cannot be manipulated, we can exclude invariant manifolds and equation-free models. The model is meaningful if it is invariant. Unfortunately, neither equation-free models nor the autoencoders enforce invariance. The autoencoder in particular only identifies where most data is in space, which is rarely an invariant manifold. Therefore, we are only left with the invariant foliation as a viable candidate. An invariant foliation consists of an encoder and a model. An encoder picks out a feature from the data that can be modes of vibrations in mechanical systems or some other invariant property. Any constant value of the encoder corresponds to a hypersurface in the space of measurements. As a measured trajectory crosses from one surface to another, the value of the encoder changes. This change of encoded values is predicted by our mathematical model. Having multiple foliations, or having learned multiple features, we can be ever more confident about the location of our observed trajectory. By working out the intersections of multiple foliations, we can recreate the trajectory just from knowing the low-dimensional underlying models and their initial conditions. A set of foliations can only become fully generative if the dimensionality of all foliations add up to the state space dimension. Invariant foliations are also unique under some non-resonance and smoothness conditions. The results are for foliations about equilibria and periodic or quasi-periodic orbits. In mechanical examples and in case of oscillatory dynamics, the model has an amplitude and a phase variable. Such model is fully specified by two functions: the amplitude-dependent instantaneous frequency and the relative damping. This holds true about vibrations decaying to a quasi-periodic motion too. Invariant foliations are the same as the joint encoding and predictive architecture, also known as JEPA, that was introduced by colleagues at Meta. They have shown that it performs better than rivals for semantic analysis of images and videos. Data comes in various forms. In order to avoid overfitting, the functional representation of an invariant foliation must adapt. For data filling the full phase space, both the encoder and the model can be nonlinear. For data that clusters around a manifold, it is sufficient to use a linear encoder and nonlinear model in the direction of meaningful dynamics, and the so-called locally defined foliation and the null model in the direction of quickly decaying low amplitude or noisy dynamics. The null model maps everything to zero. The first example is a jointed beam. The data is a single trajectory of two acceleration values. To set the initial conditions, the jointed beam is forced at a resonance peak. Before the measurement, the forcing is turned off, which leads to a decaying signal. This means that the encoder is linear, the model is nonlinear for the resolved coordinates, and for the other coordinates, a locally defined foliation is used. The result matches the reference nearly perfectly. The second example is a beam with exceptionally low damping, which means that even a single trajectory represents significant amount of data. Our result is compared with SSM-Learn with oblique projection. The invariant foliation was able to pick out the model at higher amplitudes than SSM-Learn because it does not need to discard parts of the data that contains other modes of vibration. The third example is again an autonomous system that is also compared with SSM-Learn. The experimental rig is a tank with liquid sloshing inside. The data is decaying sloshing that occurs after the forcing at the resonant frequency is stopped. Here we have three trajectories. One is dedicated to validation, which appears in mustard color in the diagrams. We are able to obtain a similar result to SSM-Learn, though it is impossible to tell which result is more accurate. The fourth example is a plate that is forced near its dominant natural frequency using two acoustic exciters at 16 Hz. This time the forcing is constantly applied and the plate is hit with a hammer systematically at 7 different points of the structure. The motion is captured by an action camera at 240 frames per second. The both displacements are extracted using an optical flow or digital image correlation technique. Two vibration modes were extracted above the noise floor at about 15.3 Hz and 35 Hz respectively. All amplitudes are in pixels. The experiment was repeated with a larger exciter, which made the second vibration mode disappear into the noise floor while also lowering the first natural frequency. A sample trajectory and the model trajectory can be seen with superposed blue and mustard lines, respectively. Note the similarity between the nonlinearities captured in the two experiments of the same rig. Multiple vibration modes could be separated from impact hammer tests of a conceptual airplane fuselage wing structure. There were 12 natural frequencies under 1 kHz. Some of the modes were easily extracted from the data, while others showed lower validation accuracy than desired. The hyperparameters, such as polynomial orders, were not tuned, and therefore the results are preliminary. The first three vibration modes are extracted with sufficient accuracy. Note that the second and third modes are very close in frequency. The fifth and the sixth modes are moderately accurate. The seventh and ninth modes appear accurate, while the eighth mode is not reliable. Note that the eighth mode has the lowest amplitude of all in the spectrum. The 10th mode is moderately accurate, while the 11th mode is not reliable. The next example uses synthetic data from a car following model near instability. The two sets of diagrams show the autonomous and forced versions of the system. In the forced system, one of the car's ideal top velocity is varied periodically. The first mode only extends up to amplitude 0.18 when the invariant manifold loses its normal hyperbolicity as the Jacobian of the system becomes singular. In the forced system, this singularity occurs earlier, and all calculations try to jump to a different mode with a similar frequency but with a much higher damping ratio. Note that for the autonomous system, the data-driven method is less sensitive to the loss of hyperbolicity than direct numerical calculations. A similar analysis can be carried out on the Show-PR system, which is the exact same system that Bettini and colleagues used to demonstrate their SSM-Learn method with oblique projection. The top diagram is the autonomous system, the bottom diagram is the force system. The data-driven frequencies match up well with the direct numerical calculation, while the damping is more difficult to capture. Note that Bettini et al. Do not display damping. In summary, we find that due to its invariance and uniqueness, invariant foliations are a sensible choice for data-driven modeling. Foliations can also pick out individual modes from messy data that no other architecture can do. Autoencoders, including SSMlearn, are neither invariant nor unique, although they can be useful if all data lies on an invariant manifold. As with any data-driven technique, overfitting should be eliminated and tested during validation. Properly setting hyperparameters, such as polynomial orders of the model and the encoder, can eliminate overfitting.